Please go ahead.
Thank you for the introduction. Let me share my screen and we can get started. Can you see my slides?
Yep.
Perfect. Okay, so today I'm going to talk to you about some ongoing work that I'm doing. It's called sparse point pillars and maintaining and exploiting input sparsity to improve runtime and embedded systems. So to get started, this is about autonomous vehicles. So I think a good question is asked, what is the state of autonomous vehicles today, right? And the answer is, turns out the tech is ready for prime time, right? It's not perfect, but Cruise as of Thursday is now actually making money in San Francisco doing robotaxi service. So where are the frontiers for this technology, right? It's to reduce latency, right? So by having a faster control system, we're able to run in a tighter loop. This is going to allow for faster reactions and improve things like safety. We also have things like reducing power requirements, right? So it turns out that in modern AVs today, a significant portion of the power budget for, say, these electric vehicles is actually going to the compute. And this reduces vehicle range and will make them, for instance, less economically viable. There's also things like reducing the power resource or the compute resource requirements themselves. It turns out they have basically multiple gaming computers worth of compute hardware in the back, and cheaper compute platforms will improve the unit economics of this. And now that these systems work, you're maybe willing to actually make this sort of trade-off between the quality of the detection and these other properties. It also turns out that AVs are not the only domain where these constraints exist, right? So you're actually able to put multiple gaming computers worth of GPUs and high-end desktop CPUs in the back of your car. But for instance, my lab has a fetch freight robot base. We're not able to strap high-end desktop GPUs to this at all. Even if we had the money and time to do this, we simply don't have the power budget, right? We have to settle for something like an onboard accelerator, like an NVIDIA Jetson, or potentially even run it straight on the CPU itself. So with that in mind, I think a question that we need to answer is, how do we reduce our 3D perception ML model resource usage? And that's essentially what I'm going to focus on today, right? At a high level, if you have machine learning models, you can sort of take a domain agnostic approach where you can do things like quantize the weights. So converting from a float 32 representation to either a float 16 or int 8, right? This saves VRAM on the GPU. It also is faster to do operations on. You can also do things like introduce weight sparsity, right? So you can take your pre-trained neural net, you can remove a lot of these weights either using structured sparsity, where you, in a regular structure, remove some of the weights. It turns out that modern hardware like the NVIDIA Ampere GPUs have support for speeding up convolutions with structured sparsity, or you can just do this ad hoc for unstructured representations. Both of these will result in faster computation. But for the purpose of today's talk, I want to focus on representational sparsity. How do you actually take the representation that your machine learning model processes and use the inherent structure found in it in order to speed up the computations you're doing? So with that, let me give you a sort of editorialized history of prior art doing this sort of representational sparsity exploitation. So 2018, VoxelNet was released. And VoxelNet, wonderful paper, very simple idea. We take the point cloud, we voxelize the entire 3D space, and we run a 3D convolutional backbone across it, right? We get out a 3D tensor, we run through detection head, boom, we get regress bounding boxes. Second comes along and says, okay, well, it turns out that in VoxelNet, 97% of these voxels are empty, and it's the 3D convolutional step that's actually dominating runtime. We could probably do something about that. And so what they do is they stick in the backbone sparse convolutions. So these convolutions are mathematically equivalent to the traditional dense ones, but they essentially allow you to skip large regions of this voxelized space by virtue of the fact that they're either all doing zero computation or a large number of the values in the convolution itself are zero. And this leads to a massive performance speedup, right? It gets about 2 times the runtime improvement over VoxelNet. And because it's mathematically equivalent, you get roughly the same detection performance. So point pillars comes along and asks the question, what if we don't slice the scene vertically, right? And so you can get essentially a pillar representation of the same thing. So if you read the paper, they actually do a nice job breaking down the various pieces of their pipeline and explaining which is, again, the most expensive components. And they get good performance in terms of runtime as well as detection quality, but we always want to do better. And so here again, you notice that, for their 2D conv backbone, 97% of the pillars are empty and it's dominating runtime. You've seen this before. And that's sort of the motivation for our work, sparse point pillars, right? Can we go in and stick a sparse backbone in here in order to get better performance? Well, turns out you do have to do a little bit of thinking about what convolutional operations you use. You can't just straight up replace the traditional 2D sparse convolutions with 3D ones in order to get performance win. And that is sort of the sort of intuition for our work. So let me dive into the anatomy of point pillars and then our work, sparse point pillars, a little bit to sort of illuminate what sort of changes you do need to make. So at its core, right, point pillars consumes a raw point cloud. It takes the 3D scene and converts it into a set of pillars. And again, most of these pillars tend to be empty, right? There's very regular structure found in LiDAR point clouds that come off self-driving cars. And so rather than trying to vectorize each pillar individually in the original tensor, standard point pillars, and then our point pillars background as well, takes this and gathers them, they call it gather step, into a non-empty coordinate format lookup matrix. So rather than representing it as a full dense matrix, you basically have a coordinate in where it would be in the full matrix, along with the points associated with it. We then run it through the PointNet style vectorizer, and we get out a sparse COO style matrix format that is what we call a pseudo image, right? It's a n by m matrix with channels that are n dimensional. In traditional point pillars, they then take this and scatter it back into a full dense matrix style representation, and then process it with our, as I mentioned before, sparse or highly dense and slow backbone. They then run this through single stage detector, which is an off-the-shelf head, and they get bounty boxes. In our work, we do not convert to this dense pseudo image representation. We maintain the sparse COO format and operate it on it directly. So this is a sort of side-by-side representation between the two backbones. On the left here, you have point pillars backbone. On the right, we have our backbone. They're both a feature pyramid style network, right? They take in the large pseudo image, and then through various stride 2 convolutions and then a bunch of stride 1 convolutions, process this, resulting in successively smaller pseudo images that they ultimately then concatenate together along the layer channel to get out their tensor. So the traditional sparse point pillars backbone uses dense convolutions all the way down, right? They do 3x3 stride 2 and 3x3 stride 1 convolutions. For our backbone, we try to be a little bit more thoughtful about the operations that we're doing in order to prevent smearing of this information, as well as exploiting it in order to preserve the sparsity for faster runtimes. So I mentioned smearing, right? So for a traditional input, imagine you have something like this, where the white entries here are non-zero entries, and the black is all 0 entries. If you run either a sparse convolution or a traditional convolution over the top of this, you'll end up with smearing of information, right? So imagine a 3x3 stride 1 convolution run over this. The neighbors to the input non-zero entries are themselves 0, but after you run a 3x3 convolution centered on this, you're going to end up with a non-zero entry. And so this results in propagation and smearing of information across the pseudo image. It turns out that there's a 2017 paper introducing what's called submanifold convolutions or sub-M convolutions, where rather than running on non-zero entries, we only center the convolutions on existing non-zero entries, and this prevents smearing, right? So these are not mathematically equivalent operations, but as a result, we're able to both exploit the input structure that has a sparsity and then maintain it across the processing. So I want to give you a sense for this visually. So this is the various pseudo images generated by the traditional point pillars dense backbone. Note that I actually had to remove the batch norm in order to visualize this, because the batch norm completely destroys any sort of sparsity in the pseudo image. But you can see here, right, again, the black background is 0 entries and the white is non-zero. The input pseudo image is actually very sparse, where you can make out the cars that are located here and some things like the buildings. As this is run through the backbone, this sparsity is completely destroyed, right? By the end here, the last pseudo image, there's almost no sparse structure left at all, right? So we need to actually be more thoughtful than simply replacing standard convolutions, standard dense convolutions with sparse ones, right? We need to use a thoughtful combination of traditional sparse convolutions as well as submanifold convolutions in order to build a more efficient backbone. And so that's what we've done, right? You can see that this is the exact same input pseudoimage, but the sparsity is actually preserved as it's flowing through our backbone. And ultimately, we get to the last stage of the backbone, and still we have a high degree of sparsity in our final pseudoimage representation. So you can sort of theoretically analyze this, right? You can say, okay, well, as a function of density of the pseudoimage input, how many convolutions do I end up doing, right? The exact same number of convolutions are run for the traditional point pillars backbone, right? It's strictly a function of the width and the height of the pseudoimage. But if you actually parameterize on density, this actually allows you to break the trade-off between width, height of your pseudoimage and runtime, because instead it's a function of actually your data itself. And so we're actually able to compute an upper bound on the number of convolutions performed by sparse point pillars. The reason it's an upper bound is we're actually assuming worst case structure in the input pseudoimage. You can imagine having pixels that are in the input pseudoimage nearby each other. Those will get merged into a single pixel in the step down of the backbone. A adversarial input would be regular dot pattern in the input pseudoimage that doesn't allow for any sort of merging. And even under those conservative assumptions, we're able to say that this leads to a significant reduction of convolutions in practice, right? So for KITTI, we're actually able to do at least 50% fewer convolutions than point pillars. This was done by taking the most dense pseudo image from the KITTI data set and then doing this analysis. And then for our custom data set Matterport-Chair, which we'll talk a little bit more about in a minute, we're actually able to do at least 79% fewer convolutions than standard point pillars. And as I mentioned earlier, the key thing here is this actually breaks the trade-off between pseudo image area and runtime, because for a lot of these newer AV data sets, they have detections out to say 200 meters, right? And you either have to have really large pillar sizes, or you need to just eat the fact that you're going to have an enormous pseudo image. This allows you to actually break that trade-off. You can have small pillars, and the fact that this pseudo image is extraordinarily sparse by virtue of the fact that it's going out to 200 meters, you're actually still able to get good performance on your sparse backbone. So that's all well and good, but if it doesn't have good empirical results, who cares, right? So we ran 2 data sets and we did an ablative study as well on our backbone, right? So on the KITTI data set, which is what was used in the original 2019 sparse point pillars paper, excuse me. So we're able to run against that as well as 3 ablative versions of our sparse point pillars backbone. And we do this on a traditional evaluation platform or a desktop with a high-end GPU. And then we also have our own data set. This data set was actually collected using Matterport 3D, and it's a chair detection task. So we actually evaluate that on a high-end desktop, as well as 2 power settings for the Jetson Xavier, which is, as I mentioned earlier, a embedded GPU style ML accelerator. And then we actually also run it on our Fetch Freight CPU, which is an Intel Core i5. So a brief note about these ablative models, right? A question that I think is reasonable to ask is, do you actually need to do all of the work that we did, right? We sat and thought about how to structure these various convolutions in order to get good runtime performance as well as quality, right? So we set up 3 ablative models. The first one, we take the first chunk from our sparse backbone, run it through these standard sparse conv, sub-mconv modules, and then plug it into the second and third dense convolutional blocks, right? Conv block 1, 2, and 3. And then we do the same thing, but we stick it in through the sparse 1 and 2, and then run it through dense 3. And the idea here is to try to get at the question, do you actually need to do sparse operations throughout the entire pipeline, or can you switch to doing dense convolutions halfway through? And then finally, one of the things you'll note here is rather than doing 3x3 stride 2 convolutions, we're actually doing 2x2 stride 2 convolutions. And the original goal for this is to prevent information smearing. If you have a single point, you don't want that to be duplicated into 2 adjacent points in your smaller pseudo image. And by doing 2x2 stride 2, you actually skip having any sort of overlap in these convolutions. However, this can actually avoid some amount of information smearing, right? It's possible that this information can actually translate across your various cells through the 3 and then the 5 and the 5 conv operations. Can we stick a wide conv in there, a 9 by 9 wide convolution as the first operation in here in order to simulate the information transfer that you would be able to get across this backbone? So this is essentially the runtime results on KITTI. If you look, we really only get very minor performance win on KITTI. And this sort of makes sense. It turns out KITTI as a LiDAR detection data set actually is pretty small, right? So we use the standard 504 by 440 pseudo image setup. This is what the point pillars paper uses. But for instance, KITTI only goes out to like 80 meters for its LiDAR data. If you were to have either a larger range LiDAR, or the other thing that KITTI does is it only typically is evaluated on the section of the LiDAR that overlaps with the 2D camera. If you were actually to use the full 3D point cloud that wraps around behind the car, this pseudo image would also be a lot larger, and you would expect to see significant performance improvements. And then I think unsurprisingly, these were never intended to be more performant, and the wide conv is significantly worse. But they do tell you that operating on sparse partway through and then converting to dense does have a significant overhead associated with it. And then also additionally, unsurprisingly, this does lead to a significant like 5 to 8% AP performance hit, because to be honest, the sparse point pillars backbone is probably harder to optimize. And the experiment with the wide convolution, I think here shows also that information smearing is not what's the result of, is not the cause of the worst performance. I think it's strictly harder to optimize as a backbone. So I mentioned that the Matterport-Chair results. So this is an image from, it's called a Matterport 3D. It's a data set of roughly 90 homes where they took 3D scanner and did, roughly photorealistic-ish scans of these environments. And so we wanted to set up a custom chair detection task, which more correctly modeled the sort of problems that are faced by service robots in order to do the evaluation on the embedded system. So we do our evaluation, as I mentioned, on a Jetson Xavier and a fetch freight robot. The Xavier is neat because it actually has 2 power modes. It has actually a bunch of power modes, but we evaluated on the highest power mode, a 30-watt 8-core mode, which it also has onboard CUDA cores. And then we also evaluated on a 10-watt 2-core setting. And we felt this gave like a full gambit of what sort of performance properties you'd expect. And then we also actually do run onboard inference on a forward pass using the CPU of our fetch freight robot. So the results here are significantly better for sparse point pillars compared to traditional point pillars, right? For on the desktop 2080 Ti, we're able to get, almost 13 divided by 20. We get a significant speed up, and this just continues across the board, right? We're actually able to get these performance wins in no small part due to the fact that the pseudo image for this data set is significantly larger, right? And the reason for this, as I mentioned, the laser scan that we're doing proportional to the grid size that we had in order to get decent detection performance is actually pretty large. A thing that I want to call out here is actually for this Xavier, on the high power setting, we're getting 163 millisecond forward pass for the standard point pillars backbone. On the low power setting with the Xavier, we're actually getting 157 for sparse point pillars. And so what this means is we're actually able to get faster, lower latency with our backbone while cutting the power consumption by a factor of 3. And the cost that we're paying for this is essentially only about 4 to 6% AP on the actual detection quality. And to be honest, I think that's like bonkers, right? For most people, this is going to be a trade-off that's almost certainly worth it, right? If you can cut your power budget by 3x, absolutely, this is something that people are going to want. So that's sort of, I think, it at the highest level. We have a project website where we provide the full paper. So this is in submission to IROS 2022. We also have code, the data sets, and actually all of the model weights that we have used in our evaluations. So with that, I think I can take any questions.
So any questions?
I have a question online.
hear me?
Yep.
Yeah, I can hear you.
Yeah, it's very interesting work. Thanks for the presentation. And I understand this is for LiDAR. I was wondering if you've considered using it for radar, because at the moment radar doesn't have a good backbone, and it's much sparser than LiDAR, right? So any comments on this?
So my understanding is that most AV data sets that are publicly available don't have a lot of radar information available in them. Admittedly, we actually only ran on KITTI data set to begin with, but certainly I think that's something that would be amenable to this backbone, right? The ability to process sparse information in a, right, assuming the bird's eye view is a reasonable representation, which, for radar it is. I think this is something that would be able to process that more efficiently. I'm actually not familiar with what people have tried to do radar processing.
Yeah, some people have tried point pillars, and some people have tried KP conv as well. So yeah, it'll be interesting to try it out on radar point clouds. For example, New Scenes has radar point cloud.
Okay, that's good to know. Yeah, we had been trying to do, or we'd considered doing follow-up work, where we tried running this on some of the newer data sets, right? The Argoverse, New Scenes, Waymo, et cetera. And, preliminary results say that this thing runs significantly faster because of this whole pseudo image to pillar trade-off.
Yeah, thank you.
So I have a question. I wanted to understand how, if you have actually evaluated the effect of point cloud resolution. For example, if you have a point cloud of a 64-layer radar and a 32-layer LiDAR, what's a significant gain do you get in processing speed? Because it seems like you're dependent now on just the number of points in your point cloud, right?
So that's true, that we're now a function of how dense your pseudo image is. The higher density it tends to be the case that as you get more dense, you're also actually able to do detections at further range. So KITTI, for instance, right, they chop everything outside of 80 meters, which for production AVs is actually not something that you're able to do, right? If you're driving on the highway, you need to be able to see things that are further than 80 meters away from you, because the speed you're operating at, you need to be able to react. As you get more dense point clouds, you're actually able to, dramatically increase the range and get reasonable looking detections. And that's where the ability to increase the pseudo image size without having a huge performance hit matters. But you're right, as if you were to say operate on a 2D laser scan, right, you're going to have a lot lower density than if you had 128 LiDAR, just by virtue of the fact that you have more points. The other thing I will say is that, natural environments tend to have a lot more structure than random point allotment. And so if you go from, say, a 64 beam to 128 beam, in practice, you're probably not doubling the density of your pseudo image, right? It will increase by some amount, almost certainly, but you're almost certainly not doubling its density. So I would not expect that if you go from 64 to 128 beam LiDAR, you'd say double your runtime. It would probably be a small change.
Yes. Thank you. Yeah, there is one question. If you could come here.
Thank you for your presentation. On slide 18 or something, where you visualize the pseudo image, I don't know which one was it. When you visualize, yeah, this one, yeah. How did you generate that?
Yeah. Okay. So basically, I took the PyTorch tensor that's being run through this backbone. This is the input pseudo image, and basically what I did is I just said, okay, for each channel, right? So it's a width times height image with some arbitrary depth channel. If any of the entries in the channel are non-zero, draw it as white. Otherwise, draw it as black. The other thing is, for this dense point pillars backbone, they have a batch norm in here, And this batch norm completely normalizes the background. So I actually had to delete the batch norm in order to actually get any sort of visualization. Or you can sort of see if you look closely here, there's the same pseudo image drawn again. For my 2D backbone, I did not have to delete the batch norm because the batch norm is actually only run over the non-zero features. So this picture was basically just literally pulling the tensor into NumPy and then drawing a visualization with like Matplotlib or something.
Okay, I have another small question. In your results, you compare to point pillar, like your sparse point pillar to the actual point pillar. But like typically when you deploy a model, like I'm nowhere an expert on model deployment, but you might take this typical point pillar and do some TensorRT optimization or some form of optimization and then deploy it. So did you do that, or is this like a normal point pillar just directly applied to your platform?
No, so this is a good question. So the original point pillars paper, they actually did use TensorRT in order to actually deploy their model, right? So you typically train using a PyTorch runtime, you then export to something like Onyx, and then you load it into TensorRT to actually get their runtime. So their ability to hit 60 Hertz was actually dependent upon using the PyTorch, the TensorRT runtime on their NVIDIA system. I did not do this in part because the sparse point pillars backbone requires you to be able to do sparse convolutions, and that required a custom CUDA kernel. That CUDA kernel does not have support in the Onyx format, and so I was not able to use TensorRT. So in order to get a head-to-head comparison, both of these are running using the PyTorch runtime. The the original point pillars paper reports that they get approximately a 40% speed up by using the TensorRT runtime. I will have you note though that this number that I'm reporting right here, this is run on a 2080 Ti, is actually faster than the number they were reporting on the 1080 Ti that they were running on using TensorRT. So I think this is a testament to the fact that while PyTorch runtime is not maybe the production system that you would use, between the hardware I used and the improvements that have happened over the last several years to the PyTorch runtime, this is still, I think, a reasonable number to reason about.
Okay, thank you. So thank you, Kyle, for being up so early. And in the interest of time, we'll move on to the next talk. And there are a few questions in the chat for you, Kyle.
Okay, I will answer them. Yeah.
Thank you very much.
Thank you.